有啊，
喂
听到。
，Hello，
呀
好不好讲话一下？
听到吗？
喂，听到吗？
听到，没问题。
OK，yes，我们Buzzcorner过后就到你啊，
OK，
听到吗？听到吗？
没问题。
很小声。呀，我这
小声吗？
呀，我就忘了100%。我们Buzzcorner过后就到你啊。
OK。
那你开一下Buzzcorner。那你跟他讲一下，开始。Hello。Hello。Hello。呀，我start Buzzcorner while waiting。为了，要不要用我的电话来做microphone嘛？连这个要关掉还是怎样？他们会听得清楚吗？我 try 一下。讲话。开始听。没有讲。Hello testing。没有。testing。testing。Cannot hear。听不到。Cannot hear if I use mic。testing。要 use mic 听不到那个麦克风。如果我这样讲就知道。Hello。test。没有啊。要来用这个麦克风啊？你要带这吧？拿着那个右边那个，拿着右边那个就行。Hello。我关掉那个，开下声音。是啊。可以听到。这个我会讲你讲。Yeah。来视频的。Hello. So now we have our Buzzcorner. Buzzcorner is actually our like news update on the latest Rust stuff. So we will like quickly talk about the Buzzcorner while you all eat. You all can just like focus here a bit and you all can talk as well. 没有声音了这个。没有，要右边。我放过来。Yeah, so the latest Rust update is Rust 1.93, which allows one of the things is which allows the global allocator to use the thread local storage. What does that mean? The global allocator is like the allocator where you allocate the memory by default. Unlike Zig where it has you can use custom allocator everywhere. Rust uses one global allocator by default, and you don't have to pass that everywhere. Although in some parts you can say you want to use a different allocator. Like for example, usually people use a system allocator which is like the glibc allocator. And the next thing is you can use CFG attributes on ASM lines now. ASM is to let you write assembly out in Rust using a macro. And now in the macro you can say for certain target features like you see here on SSE2, then you can support you can just enable it or not. And the next thing is Chrome team will be doing the Google Chrome, right? They will be doing a 1% rollout for Rust-based XML parser. So they will be starting to use the Rust XML parser to roll out on Google Chrome. The only thing they are worried is about the performance parity, but otherwise everything else should be similar. That's just their worry. So they will be rolling out 1% for production. And next thing is Xiaomi HyperOS 4, which is the newer Xiaomi phone. They will be using the Xiaomi HyperOS is the Xiaomi operating system on Android. I mean their MIUI thing. Previously it was called MIUI, but then now they call it HyperOS. Their newer version, the 4, which is to be released in August, they say they will rewrite the stuff in Flutter and Rust. Yeah, so that's Xiaomi. But so far, besides Xiaomi, right, the other stuff that use Rust is the Vivo Blue OS, which they uses Rust. Vivo. And Android-wise, Google uses Rust for like the Bluetooth tag, I think. But in the kernel side, but not this one. I think they are building it for the application side, like the system tools.
Is the whole OS using Rust or just like parts of it?
I think parts of it, because Xiaomi uses Android, and stock Android, some parts of it is written in Rust. Yeah, same like Linux kernel, some parts of it is written in Rust. Yeah, recently there's another news where Linux kernel, they say Rust is no longer experimental, they'll just roll it out. Yeah, it is they completed the experiment, so they decided to continue using it. Not just Linux, I think Windows also uses Rust in some of the parts. No, I don't know. And another thing is the Rust at scale. Rust is going to use, yeah, for WhatsApp, right? They are changing Rust to use in some parts, but I don't really know what parts are there. But yeah, but WhatsApp is going to change some parts to use Rust. I think a lot of these companies use Rust for security purpose. Yeah, security purpose, because they say Rust is memory safe, and then you can get, if something happens, then you get panic. Instead of like you leak the memory or somehow, then in C++ people get memory vulnerabilities. So Rust doesn't get that. Like Chrome team says they get like 30%, 70% or 30% lesser memory bugs. Yeah, memory bugs, which is a very high priority safety bugs, the CVE, those kind. And then this one is on Burn. Burn is a Rust like ML framework or something like that. So now with their 0.20 release, they support unify both GPU and CPU kernel with kubectl. So means one code base can write code that can run on both CPU and GPU, or maybe at the same time. But I don't know what's the use case for that. But so it's simpler. You write your code once for CPU code, and then it will work on GPU as well. And you see the benchmark here. The benchmark on the left is a CPU benchmark, and the benchmark on the right is a GPU benchmark. So they are competing with LibTorch very closely. For you see the blue one is the blue one is a kubectl, and then the bottom one is a LibTorch, which is a Python source library. And the left one, like the CPU benchmark, it looks like Burn is performing quite well comparing to like what is that? Yeah, Python has a LibTorch and ND array. Yeah, it's performing quite well compared to them. And then lately releases, there's a Scheme. Scheme is a file finder library. Like, do you want to know FZF? Yeah, Scheme is a FZF clone in Rust. And then there's also Zero Brew. I haven't tried this yet. Does anyone here know Homebrew? Homebrew, the package manager for macOS. Yes, Homebrew. So Zero Brew is like a drop-in replacement that's 5 to 20 times faster, but it's experimental. The design is basically based on UV. You know Python UV, right? The UV package manager, the very fast pip alternative. So Python have a fast pip alternative that a lot of people are switching to it. I think I also use it on work, where you build stuff, it's like so fast that I can build everything in like 10 seconds or 30 seconds due to caching and stuff. Yeah, Zero Brew takes inspiration from UV.
This is the access.
Yeah, so previously the access have hot reloading, but hot reloading just happens on the top crate, so it's like on the main RS only. If you have like lib RS, or if you have a workspace with multiple crates in the workspace, then you can't really hot patch the things inside the other sub crates. So now they claim that they fixed it with this PR. I just saw it today actually. It just happened today. It's just merged today. And hopefully you can now hot patch Rust code in the entire workspace. Yeah. And then we have Bevy 0.18. Bevy, if you don't know, it's a game engine. The logo is basically here. So basically, it's a game engine written in Rust, and in Baby 0.18 we have for me these are the three major updates. We have like full screen materials. So basically, you can create. Previously, if you want to create full screen materials, you need to set up like custom pipelines, post-processing pipelines. Now you can just create a material and then implement some traits, and you get full screen material. And then we have solar improvement. This is like the global illumination thingy for Baby. These are like some improvements they made. I'm not sure what improvements, but it looks much better. Yeah, it's a ray tracer thingy. And then Baby Feathers, this is the UI experimental UI kind of create by Baby. I think it's used for their like Baby what do you call it? Baby editor prototype. And now they have a new widget called color widget. Yeah, not much. Yeah, sorry.
Do you know that you call it from the terminal? To like get the widget?
Sorry?
Can you call it from the terminal?
No, I don't think so. This one runs on like an actual native app. Like.
I have.
And then if you don't know about Velo is like a compute-centric vector graphics vectorizer, a renderer, or you can say it's a renderer. Basically, you can provide SVGs or maybe drawings of like DXF or whatever, and once you convert it into Velo type, you can render it. So basically, the cool thing about Velo is that it uses GPU to render the graphics. So it's extremely fast. You can render a large scene of vector graphics, and it takes just milliseconds of it. And previously, it only runs on GPU, so you must have a GPU. So if you want to render it on, let's say, on the browser, you must have web GPU embedded. Because it's not that you can't use GPU on website, it's just because you can't use compute shaders in website, in browser, sorry. So you must have web GPU in browser to be able to run Velo. But now with Velo CPU, you can run a hybrid mode, so you get to use the CPU for those that you can't use, and you get to use the GPU for those you can. So yeah, you can run Velo on the browser right now. I feel like it's possible. I'm not sure if there's a demo right now, but it's possible. This is something I saw on LinkedIn. If you are not aware, there's a company called Vectorware. They are like a company that focuses on GPU, and one of their mission is to enable GPU to run Rust code. So this is like they have been doing for quite some time, but this is quite recent, which is that they enable you to code GPU code in Rust, and you can, and in addition to that, because previously their only solution is that you are limited to no STD, which means you can't use the standard library in Rust, so you can only use the core library. Now they somehow managed to get STD library inside there. I think there are also some caveats, so it's not everything running on the GPU from the STD, so they have like some parts that are still running on the CPU that can't be run on GPU. Yeah, but it's kind of a breakthrough that you can write everything in just Rust. Last thing, we have a WhatsApp group called Baby Malaysia. It's not a cult, it's a community. And please join. Thank you. I haven't eaten. I want to eat. Okay.
So we can start the second round.
You finished?
First, let me. Hi. Now it's a pop. The other speaker talk. I think you all can come in. Can listen, and then we wait for the talk. Hello, Paul?
Hello? Yeah, you ready?
Yeah, I think you can start from the first slide. Yes, yes. Can you full screen? So it's bigger.
Yeah. Should I start now or wait a few more minutes?
Can you full screen the? Can you full screen
Yeah,
the?
yeah,
Yes.
yeah.
Yeah. Thank you. Yeah. You may start.
Okay, cool. All right. Hello everyone. My name is George. I'm from Compile. So today I'll give a speech on Compile, which is an async runtime for Rust. The main authors of this library first is Verisoft, but unfortunately he will not be here today. So I'll give the speech today. I'm from University of Maryland. I'm a master student in computer science. He's a PhD in physics from Tsinghua. Okay. Now, first I'll introduce async Rust briefly. Okay, so here's a very simple blocking example of creates a socket, a TCP socket, and reads some data from the connection. So first you bind the socket to your AD ports locally and create a buffer on stack, and then run the loop that each time you accept the stream and you read some bytes from stream and do something with it. It's a pseudocode, so but problem is accept and read happens actually they are sequentially. So when you accept, you cannot read from the socket and vice versa. What if we turn it into an async version? So we turn the function into an async function and set on a wait to each of the IOs. But the problem still exists. It's still sequential. You accept and then you read, and then loop. Now, async with concurrency is actually what makes this really useful. We can here you can see there's a spawn here. Oh, sorry. There's a spawn here, which means you effectively delegate to background. You run the task in background without blocking the main task. So each time you accept a stream, you spawn a task out, run it in background, and you can keep accepting new streams, etc., which increase throughput significantly. Okay. So under the hood, async Rust builds around this single trait called future. If you don't know what a trait is, it's basically like an interface or abstract class if you are from OOP. This trait has one associated type, is output type. Oh, you can see. So each of the await or async functions here outputs some results. So the result will be their output type. And one function called poll that returns this enum poll with two variations. One is ready and one is pending. When it's ready, it gives you a value of type t. That is the output of the future. The trait represents the operation will complete or return ready sometime in future. If it's not ready, it will return pending. And obtain a waker from the context. You don't actually need to know what they do. You just need to know that waker can be used to notify the runtime later when it's ready. Hold again. This whole design effectively gives up the thread or yield to other tasks until they are being pulled again. And compiler will generate a future type, an anonymous future type. So you cannot write out the type, but you know it's a future. For each of the async function you write. Okay, now entering runtime. Runtime is, I say, you IO and executor put together to get a runtime. So the executor, the future I mentioned before will only progress when they are polled. This is a really simple single loop executor that posts the future and posts the IO in one single loop. So first we create a waker and create the context from the waker. Uh, and then we pin the future on the stack. You don't really need to know what pin is. And we poll it. If it's ready, we return the result, and that's it. If it's not, we continue to poll the IO. Okay. And then when we finish with the IO, we come back and we poll the future again. That's basically just one single main loop. And IO. That's the interesting part with runtime. There are two types of IO, I should say, two main types. One is we call it poll-based, and one is we call it completion-based. If it's a poll-based IO, we call the driver a reactor, and if it's completion-based, we call the driver a proactor. With poll-based IO, at the beginning, you register a file descriptor with the kernel, and you wait for kernel to tell you if that file descriptor is ready. So when you poll the IO, you're checking for readiness notification, and when some of the file descriptor is ready to read or write, you perform the actual blocking IO yourself. But you know that syscall will not block the thread, so it's pretty quick to call and pretty quick to return. Some examples include epoll from Linux, KQ from actually we mainly use it for Darwin, but it's from BSC, and poll from POSIX. And then completion based. With completion based, you don't check for readiness and perform the IO yourself. You just submit the IO request to the kernel, include the buffer, include the file descriptor, and everything needed for the kernel to perform the IO for you. And when you poll, you're checking the results. So you actually are handing out your ownership of the buffers to the kernel. Before it returns, you cannot copy it, you cannot move it, etc., etc. And examples include IOCP, and IOCP is from Windows, and IOUring is from Linux. It's the new thing in the town. Here's a very, very simplified figure that compares blocking, poll-based, and completion IO. So with blocking, you can see these gray strips that blocks the threads without doing anything useful. That decreases your throughput, your performance. And with Reactor, first you register all your file descriptors, and then yield. So when you yield, you can actually do other things in that thread. It's not blocking. I just didn't put anything here, but you know it's that the thread is actually doing other works. And then when the file descriptors are ready, you perform the blocking IO, but it's not actually blocking because you waited first. And then with Proactor, it's almost the same, but the IO part is done by the kernel, so it will give you the result directly. You just handle the result. Yeah. Okay. And the go-to option when you want async runtime now in Rust is Tokyo. It's poll-based. They have a library called Mio or Meal that wraps around the epoll and KQ I mentioned earlier, and use that to perform IOs. They use what we call work stealing scheduler to balance load across threads. So by default, they have multi-thread runtime, but that requires certain sync when you spawn a task. Basically, meaning it has to be multi-thread safe, right? You have synchronization, cross threads, you have logs, you have atomics, uh, and that actually reduces locality and predictability. So sometimes you have very unpredictable performance. But in general, it's a great choice, a great general runtime. Now, introducing compile, the main topic of this presentation. It's completion based. We use IOURAIN on Linux when it's ready, and IOCP on Windows. Um, and we fall back to Pobase on other platforms. It's mostly local or share nothing. We call it share nothing or thread per core, because each runtime will only run on single threads, and with Spawn we you don't need send or sync. You can have like ref style or some very single threaded primitives. You don't need to have logs in your future. So that creates low contention, you have better locality and better predictability. And also we have an optional global dispatcher to load balance. For example, you can have a TCP stream, actually TCP socket on the main thread, and when you have new streams income, you dispatch it to different threads and run that connection in that thread until it's finished. Here's an example of the compile driver. It's So first you create the projector, and you attach your socket to that projector, and then start to receive it. So we have different operations that can be used to push into the projector. So here we are using receive. So we receive some data from the socket. Here socket, buffer, and some flags. So when you push it, it will give you two potential results. One is that it readies instantly. So you don't need to wait for anything. It's just ready. If it's ready, you get results. You're done. If it's pending, it gives you a key that you can use to check back later. So you said each time you pull it, the projector pulls the kernel for results, and then you try to pop it to pop the result from the reactor with the key you get earlier. If it's ready, you break out, you're down. If it's not ready, you loop back. That's the reactor or under the hood runtime. Yeah. Cancellation safety. It's a pretty hot big on anything Rust. So in POP-based IO cancel, you don't actually need to cancel anything. You just don't do the IO when you get the readiness notification, and that's it. You have canceled the operation. But in completion based, because you hand out the IO, you hand out the buffer to the kernel. Kernel is doing the IO for you. Cancellation is asynchronous, so you need to tell the kernel to stop doing that IO before it's too late. But there's still chance that you cannot cancel because the kernel has done too much progress already. So cancellation in completion-based I/O is not reliable. Sometimes you still have the I/O being done, even you request this to be cancelled. Here's the example where the cancellation is needed. Still TCP socket bind and accept some thread, sorry, some connection, and you have a timeout. So before the timeout runs out, if you get the client, you handle the connection. If it's not, then what happened? Because there's might be still be a client pending in the task in the kernel. How do you handle that current, that connection? You need to close it, right? Yeah, that's why cancellation is needed. Um, yeah. And then always forgettable. That's the fundamental design of Rust, fundamental design of Future. Normally, Future in compile tries to clean up operation when they are get dropped, but job is not really reliable in Rust because forget is always safe, and you can actually, even if forget is not safe, you can create a leak with just some RC reference counted. When you have a cyclic reference, you are effectively leaking the whole RC. A reactor will only access the buffer synchronously, so there's no problem, no issue with the forgettable in here. But with the reactor, with the completion-based IO, because you are submitting the buffer to the kernel, as I said, you cannot drop it, you cannot move it. If you leak the future and then you drop the buffer might still be using in the kernel. If you drop it here, that causes use after free inside the kernel. Actually, that's even worse than you yourself use after free. So the solution for now is to pass the ownership of the buffer into the proactor, and we will keep it in the heap to ensure it won't be moved or dropped before the operation is ready. And when it's ready, we will return the buffer back to you. Yeah. Conclusion. Asynchronous Rust provides some highly customizable mechanisms, i.e., future for parallel I/O. And based on the parameters, the IOV and IOCP compile provides a completion-based async runtime and makes high concurrency more efficient. Completion-based asynchronous I/O does require some evolution of Rust language. We need to solve the two issues I mentioned earlier. One is cancellation, one is forgetfulness. And yeah, that's it. Thank you.
Yeah, so is there any questions for George? Yeah, George, can you hear us?
Yeah, I can hear you.
Yeah, is there any questions? I think I need this mic.
Hi. Just now you mentioned that canceling may cause use after free. So, is it a soundness problem in cancellation, or is there an unsafe somewhere?
Actually, use after free is not caused by cancellation. Is by merely like because in Rust, if you still have the ownership, you can drop the buffer. But in reality, you are hand out the ownership to the buffer. Means you cannot drop it before the action, the operation completes. Uh, so yeah, these two sides are not related actually. So if you are only handing out a reference to the buffer, Rust will not prevent you from dropping the buffer before it's returned. Uh, that creates the use after free. Uh, yeah, it's pretty unsound. It is.
So, so, so meaning is that a soundness problem in the language?
Yeah, that's a soundness problem. Not with Rust. It's just because the how the I/O works. Yeah, the Rust itself is good.
Yeah. So the program, the function that hands it over should be marked unsafe here, lah. This is a
Yeah.
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 Okay.
Right. There's another potential way to do this, which is to mark everything unsafe. But that will be very bad to very bad to use if you think about it. Yeah, turning everything safe is not actually what we want, right?
I have a question regarding passing ownership between application kernel. So I see this. I think it makes sense to pass ownership for like read and receive operations. We want like exclusive ownership of this buffer for like write-like operations, or I mean read-like operations where we fill the buffer. But I see concerns with operations like send or write, when basically we want to, so we have some data in buffer and we want to do some I/O. And technically we could do like concurrent I/O with the same buffer. For example, we could send this data over network and concurrently write it to disk, even maybe in multiple copies, but with ownership passing interface in that it doesn't allow to do concurrent I/O. So it only supports only one operation, the type which is a buffer.
Yeah. Actually, do you know Bytes? It's also from Tokyo. It's like it's like a reference content bytes. It's like you wrap RC around the bag bytes. You can use that to have multiple references to a single buffer and also have the ownership of that buffer. Um, yeah, compile supports bytes and you can use that to do concurrent writes to multiple I/O.
I have a question here. So,
Yeah.
like, I heard like using computation-based I/O is like faster than the alternative which Tokyo provides is pole-based I/O. But like, why isn't like people using it everywhere like Tokyo? Like, if it's like faster and it reduces like the operations, like I think yours supports the batch operation that IO Uring supports, right? Like instead of submitting one task one by one, you submit like batches of tasks using a single syscall, which will be like reducing the syscall overhead. Like if that's the case, like it sounds better, but why isn't people using it?
So first of all, um, compression I/O exceeds pole-based I/O mainly in file system use cases. So you write a file, etc. Because with Tokyo, all the async file system operations are actually blocking uh, at the background. They use a thread pool to block the to do blocking IOs with file system because there's not that much async. Yeah, EPO doesn't support that basically. Um, with IO range, you can do actual async IO with file systems, and with network, I say they are probably the same performance when you compare completion IO and pole-based. And then the issue is because pole-based IO is so much more mature compared to completion IO. The Rust future is designed around pole-based IO. You can literally future has a function called pole, right? So the ecosystem and the whole language is leaning towards pole-based IO, and Tokyo, the main runtime, builds around pole-based IO. That's the tendency of the language. So I think that's why most people won't use pole-based because completion-based. Sorry. because it's just too much more effort to spend if you want to use completion-based IO. But we are trying to reduce the friction to get onto completion-based IO, and I hope everyone can someday try it. Yeah.
Is there anyone else that have any other questions? Yeah, so now no more questions on our side. Yeah, thanks Josh for